Welcome to The Explainer. Let's just dive right in. Today, we're looking at the hidden mathematical rules of nature and how those exact rules govern where, why, and how species survive on our planet. It's kind of like a giant puzzle, really, and it's a fascinating journey that literally starts out in the middle of the ocean, but ends right in our own backyards. So, what does a remote Pacific volcano have in common with your local city park? I know we're starting with a pretty bizarre question here. What could a flooded volcanic caldera out in the Pacific possibly have in common with that little square of trees down your street? Well, the answer to this actually reveals the ultimate blueprint for saving species across the globe. Because to nature, both of these places are islands. Here's exactly how we'll unpack this journey together today. First, the science of islands. Then, single large or several small. After that, the fragmentation problem. And finally, restoring biological connections. All right. Section 1, the science of islands. Let's start with the baseline and look at literal oceanic islands first, like Maug Island in the western Pacific. So, back in 1967, ecologists Robert MacArthur and Edward O. Wilson discovered that patterns of biodiversity aren't just random. They actually created this quantitative framework called island biogeography. What they found is that the number of species on an island is a dynamic balance. You see, it's a continuous tug-of-war between the immigration of new species arriving from the mainland and the local extinction of species that are already there. It's just this ever-changing equilibrium. And the absolutely crucial point of all their complex math translates into this stark, simple rule of thumb. Reducing habitat area by 90% will roughly halve the number of species it can support over the long term. It's wild, right? This comes from their core empirical pattern, the species area relationship. Very simply put, larger islands consistently support more species than smaller ones. Now, this brilliantly illustrates the second dimension they added, isolation. A large island that's close to the mainland, it absolutely thrives. It gets lots of immigrants blowing in by wind or drifting on water, pushing it to a high-richness equilibrium. But on the flip side, a small, remote island really struggles. Way fewer species arrive, and because the space is so small, they compete way harder for limited resources. That drives up the extinction rate, so it settles at a low-richness equilibrium. Section 2, single large or several small. This whole island theory didn't just stay out in the ocean. It actually sparked ecology's greatest puzzle, the SLOS debate. That stands for single, large, or several small. Imagine you're a conservation architect, okay? You've got a fixed, limited amount of land you can protect. Do you put all your eggs in one basket and build one massive park? Or do you spread those resources out and protect a dozen smaller patches of land? Well, a single large reserve is incredible for supporting top predators and wide-ranging animals that just need massive territories. Plus, it really insulates the deep interior habitat from invasive species. But the disadvantage? A single catastrophic wildfire or disease outbreak could completely wipe out the entire protected population. There's no redundancy. On the other hand, several small reserves protect a much greater diversity of habitat types across a whole landscape. You get multiple populations. But the downside there is those individual fragments are just too small to sustain large-bodied species, and isolated populations can definitely suffer from inbreeding over time. Today, the consensus is actually a synthesis of both, which we'll get to in just a bit. Section 3. The fragmentation problem. Let's pivot from the literal ocean to the figurative islands scattered right across our continents. Because real-world conservation rarely involves pristine oceanic islands. Instead, we're dealing with habitat fragmentation. This happens when continuous forests or plains are carved up by roads, agriculture, and urban sprawl. And it's absolutely critical to understand that fragmentation doesn't just shrink the total area of the habitat. It fundamentally changes the shape and the character of whatever is left behind. And that brings us to a pretty harsh reality. It's not just about losing space. It's about the dangerous new borders we create. We call this the edge effect. You see, every fragment has a perimeter, where the natural habitat abruptly transitions into something entirely different, like a paved highway or a farm. And the edge is a brutal place. Along that boundary, you get a really harsh combination of higher temperatures, increased wind, and much lower humidity. It completely alters the environment. Plus, it essentially creates a fast pass for generalist predators and invasive species to just march right into the habitat. As a forest fragment shrinks, the proportion of it that's influenced by these harsh edge conditions grows rapidly. Take a ground-nesting bird, like the warbler, for example. This bird is an interior specialist. It literally requires cool, dimly lit forest floors to survive and safely raise its young. So for a bird like this, a small fragmented forest is a total nightmare. Why? Well, because by the time you account for the higher temps and the predators pushing in from the edges, the functional, safe area inside that forest is actually far, far smaller than the geometric area you'd see on a map. Moving on to Section 4, Restoring Biological Connections. So how do we fix this fragmentation? How do we stop the resulting inbreeding, the lack of gene flow, and the slow march toward local extinction? Well, I want you to let this quote sink in for a second. Connectivity is a conservation resource as tangible as area. This is that modern synthesis I hinted at earlier. If reducing habitat area incurs an extinction debt, we can actually offset that debt by linking these fragmented islands back together.
We achieve this using biological corridors. These are strips of natural habitat that connect otherwise isolated fragments. They're literal bridges. They allow isolated populations to mingle, breed, and ultimately survive. If a population in one fragment dies out, animals from a connected fragment can just move right in and initiate what we call a demographic rescue.
And we aren't just theorizing here. The empirical evidence totally proves these work. Just look at the studies on mammals in the fragmented forests of the southeastern U.S., or birds in Australian eucalyptus woodlands, or even large carnivores using dedicated wildlife overpasses in Banff National Park. They all consistently show that corridors increase movement rates and genetic exchange. Now, sure, reserve designers do have to be careful because these same corridors can sometimes facilitate the spread of disease or invasive species. But overall, they're an absolutely essential tool. Perhaps the ultimate real-world application of this whole concept is the Yellowstone to Yukon, or Y2Y, initiative. This is a massive, highly ambitious project aiming to link protected areas all the way from Wyoming up to the Yukon through a mosaic of corridors. It's MacArthur and Wilson's island biogeography applied on a massive continental scale. To wrap up this explainer, I'm going to leave you with a final puzzle to test your own understanding of edge effects and area. Think back to our ground nesting warbler and consider the shape of the habitat, not just the total acreage. Would an interior specialist bird survive better in a square forest or a long, thin corridor strip of the exact same area? Which shape maximizes that safe, deep interior, and which one is almost entirely made of dangerous edges? Think on that. Thank you so much for joining me for this explainer, and keep looking at the world through the lens of these hidden rules.